Simplifying radical expressions is a skill that we use whenever we're given a square root or radical problem that doesn't evaluate to be a perfect whole number answer. So to begin, we take a problem, like for example 125n, the square root of 125n, and first you factor completely the coefficient or numerical part of it until you get down to its prime factorization. So I would be asking myself what two numbers multiply to make 125, and I might say, well, 5 and 25 multiply together to make 125. Now 5 is a prime number, so it cannot be broken down anymore. I'll kind of underline it so that I remember to use it when I write out my factorization. 25 can be broken down further. I would say it's the same as the product of 5 and 5. Again, since 5 is prime, I'm going to underline both of these, and that tells me that my prime factorization for 125 can be rewritten underneath this radical as 5 times 5 times 5. Now go back up here to this variable n. Sometimes we see it with an exponent, but in this case you'll notice it doesn't have one. That's just because it's only being multiplied underneath this radical one time. So I would write it being multiplied out one time in my factored radical down here. After I've factored the radical completely, now I'm going to go through and I'm going to look for pairs of common factors. And I'm going to highlight. I see a pair of 5s, and that's actually the only pair that I have, but that's okay. And so I say, well, since this pair of 5s shows up underneath the radical, I can take those out of the square root, which would result in just one 5 being written on the outside. And then underneath the radical, I would be left with, instead of 5 times n, I'm going to write that in a simpler form to be just 5n. And so then the simplified version of this non-perfect square root is this answer right down here. We would read this as 5 root 5n, or 5 times the square root of 5n. To show you another example, we'll go through a problem that's got a slightly bigger number, because I know those are sometimes harder to work with. So let's say that the problem we're given is the square root of 512 times k to the power of 2. Again, I'm going to treat the numerical part and the variable part separately at first, but you'll notice that I write them all as part of the complete factorization later on in the problem. So the problem that I'm looking at right now is trying to find two numbers that I know can multiply together to make 512. Since I see that 512 is an even number, I know that it is divisible by 2. And if I were to work out what 512 divided by 2 is, I would find that it breaks down to be 2 times 256 for the factors that I break down 512 to be. 2 is a prime number, and so I'm going to underline it. It's going to be included in part of our factorization later on. But 256, again, with it being an even number, I know it can be broken down to be something smaller. It would again be 2 and something being multiplied. I would divide 256 divided by 2 to get the other factor here to be 128. I'm going to underline another factor, another prime factor of 2 that shows up right here, and keep going. Because again, 128, that's another even number. Any even number larger than 2, I know can be broken down to be the product of 2 and something. In this case, it'd be 2 and 64. And so I'm going to underline this third factor of 2 that's shown up. Keep going with 64. This time I'm going to break it down. Maybe a more common pair of factors you know for 64 would be 8 and 8. But then 8 can be broken down as 4 and 2. So I write both of these as that breakdown. And then 4 can be broken down to be 2 and 2. And so again, I'm going to go back and underline. Here's all of these prime factors of 2 that showed up from this problem. I'm going to need to make sure I include them all in my factorization. And so I'm going to write under kind of a larger radical now that we have broken 512 to be a total of, if I count them up here, 1, 2, 3, 4, 5, 6, 7, 8, 9 factors of 2. And so I know it's kind of cumbersome, but I write this out: 3, 4, 5, 6, 7, 8, 9. And then don't get too lost with this work. We also have to go back up and consider k to the second power. This exponent of 2 means I need to write out 2 factors of k that are also being multiplied underneath this radical. Now I know that looks like a lot, but at this point we're ready to maybe take a highlighter, or you can even just circle them or underline them and find pairs. And so I have one pair of 2's here, I have another pair of 2's here, a third one here, a fourth one here, and that would leave me with this one little guy left over. And then I also have this pair of k's. And again, since each of these shows up as part of a pair, they can get taken out one at a time from the square root to be 1, 2 from this pair, another 2 from this pair, another from this pair, and another from that pair, as well as then 1k from that pair that was inside. And again, I move them out of the square root. If there were 2 inside of the square root, it shows up as just 1 on the outside. And then underneath the radical, what I'm left with is just that lonely little 2 right there. To simplify to our final answer here, we would say all this stuff that came to the outside of the radical, I can kind of put it back together to be a little bit simpler in my final answer. This would be the product of 2 times 2 times 2 times 2, which if I multiply that out, I get 16 multiplied by k, and that is also multiplied by the square root of 2. So final answer for this one worked out to be 16k square root 2. One more example, getting a little bit more complicated here, would be if I had, say, oops, sorry about that, didn't mean to keep it in a highlighter. Let's try that again. If I had a problem like this one, where it said 200 m to the 4th n. Okay, so in an example like this, again, take the numerical part, factor it. First thing that jumps out to me from 200 would be 100 times 2, which 2 is prime, so I underline it. But 100, I know it's going to break down to be 10 and 10 maybe. 10 gets broken down to be 5 and 2 in both of these cases. And so all of these would be my prime factors. And so I'm going to write them out underneath a larger radical here. I like to go in order from least to greatest, kind of ticking them off on my paper as I go, so I know I counted them all. So I have a 2, and a 2, and a 2, and a 5, and a 5. And then go back up to your variables. M is being raised to a power of 4, meaning it would be multiplied out 4 times. And notice that the n doesn't have an exponent that we can see, but that's just because it only gets multiplied out once. Now go through and look for your pairs. I have 1 pair of 2's, 1 pair of 5's, and 2 pairs of the variable m. And so again, the pairs from the inside of the radical, when I take them out of the square root, I will write 1, 2 from this pair, 1, 5 from this pair, 1 m here, and then a second m from that second pair. And underneath the radical, I'd be left with 2 multiplied by n. To clean this up just a little bit, we'll say that the stuff here on the outside, 2 times 5, we can write that in a simpler form to just be 10. And m times m, I can rewrite that in a simpler way to say m with an exponent of 2. And then again, the radical portion that's left over is square root 2n. So altogether, our final answer here would be 10 times m squared times the square root of 2n. And that's just a few examples. Some of them you may have seen done in class, others of them may be new to you, but that is a brief summary of how to simplify radical expressions.